The work done by a force is very simply the magnitude of the force is parallel to the distance times the distance. And graphically, we could think of force versus distance. And if the force is nice and constant, then this works very nicely, and that the area under that curve is the work. Now, that is when this force is a constant value over a given distance. Now, the spring was not not a constant force, but our spring force actually depends on the stretch or compression. And so we saw that it was a nice linear function, and that the spring force is Kx, where K is what we call our spring constant. And the spring constant is a number, kind of like the coefficient of friction, where it describes some quality of the spring. It's measured in newtons per meter, so unlike the coefficient of friction, it does have a unit. So it tells me how much force is needed to stretch or compress the spring per meter. And so that's our unit for our spring force, our spring constant, K. Now, if the area under the graph is the work, in this case, the area under our graph will not be constant. I can't just use the spring force value at a particular distance, because the spring force magnitude was changing. So I'd have to find the area under that curve, and conveniently, the area of that is a triangle. So 1/2 base times height, whatever the spring force is. And if the spring force is defined as being Kx, I could substitute that in, and I'd have x and 1/2, and that would give us 1/2 Kx squared. That winds up being pretty neat and easy. However, not all of our forces are constant or even linear, like the spring. A rubber band will act like a spring, and then it will begin to not act like a spring anymore. So I could actually use the integral of the force with respect to position as being our work function here. So then here, if I use our spring, going from 0 to x, Kx dx, then we would have Kx squared divided by 2, evaluated from 0 to x. And I know it's not typical to have the variable and the limits to be the same letters, but we do that in physics a whole lot. So then minus 0, and that is the work done. Now, we are going to treat springs as being conservative. And conservative forces, remember, the work done by the gravitational force is equal to the negative change in the energy stored in the gravitational field. And the gravitational force is what we call a conservative force, because it doesn't matter the path taken. So that means that for the gravitational force, we could have, here's the ground, and here is the tabletop, and we're going to move this object from the ground to the tabletop. And we could take this path here, or we could take this path here, and it does not matter which path we take, the work done, the net work done by the gravitational force will be the same, and our change in gravitational energy will be the same, because the energy only depends on the change in position here. So for most of our problems, we will consider the spring to also be a conservative force. So that means that the work done on a spring will be equal to its negative change in energy stored in the spring. Now sometimes you'll see this as the energy spring or the energy elastic, because springs are considered elastic. So the area under the curve represents the work. Now, in order to stretch the spring, in this case we're stretching a spring, we were applying a force. So if we have our floor and a wall and a spring and a block, and we're going to have to pull it to the right force to get it to stretch this positive distance. So this will be a positive change in position, and this will be the direction of the force that's applied. And we are doing positive work, okay? And then, but the spring the whole time is opposing us. So as we pull, that spring force is going to increase and increase and increase, like we see here in the graph. And that spring force will oppose. So the work done by the spring is actually negative while we expand the spring. So the work done by the spring is negative. So let's look at this. So as we pull the spring, so pulling the spring causes there to be negative work done by the spring force. So the puller is doing positive work because the pulling force and the displacement were parallel to each other. But the spring force was negative, it was pointing to the left, while we were moving it to the right. And so our negative spring force times our positive displacement means that the work done by the spring is negative. So if the work done by the spring force is negative, then that means that the energy stored in the spring would be positive. So this results in a positive energy change in the spring. So it's just like these signs have flipped sides here. Okay, so when we stretch the spring, we do positive work and we are adding energy to the system, and the spring force is doing negative work. And so that is how that negative sign works up there.